Now, these cases here, you can see this is the dam failure I told you earlier. You know, this picture here on the right will give us a very clear results how the water is going through when the dam failed in one of the cities in France. The village was destroyed behind the dam, as I mentioned earlier, because of a very short time and high speed of the water. Now, you see some of the softwares here, they are considering similar problems within the rivers. Maybe in India, you have a lot of agricultural lands and agricultural areas. During the rainy season, it will be affected by the river. And that's because the water in the river rises and will cause flooding to damage the floodplains on the right and the left of the rivers. This is a major problem. For you as a student, as a civil engineering trainee, you need to understand how you simulate a work within those rivers in India to overcome this problem, to design a different channel in the rivers. So when it's a very heavy rain, then you will not be affected by the flooding. Now, this is just a simple example of the river here. You see how you can design a channel in India within the rivers when sometimes have problems during flooding, to measure the velocity, the speed of the water, and the channel depth and width. So basically, we try to talk about this example in practical, not only theory by this picture. Now, in practical, we have the idea, we come up with the design, then you try to innovate this into CFD work. The CFD is how to come up with the geometry of the area, the river, the depth, the width, which we say the width, the length, the depth of the river channel, and the speed of the water, what is inside the river. It could be sediment, it could be gravel, it could be sand, it could be small trees, grass, vegetations. All these can be considered to solve such a problem by having this example here. So what we have done here, we considered a river channel. Imagine this is a 3D river channel. I give you this example just for you to understand. So if this is your river and you have some kind of different bedding in the river, so it could be anything, it could be big rocks, it could be small vegetations. This here is a small cylinder. Imagine this is a vegetation. So our simulation work is concentrating on different bedding. It could be vegetation, but we consider it as a small, tiny cylinder here. We try to implement this case study here by having a river channel. Inside the river, lots of vegetation exists. When the rain starts, this vegetation slowing down the water in the river, what will happen? The water surface rises and it will go out of the left and the right, then causing flooding. All the houses nearby, all the agricultural lands nearby will be affected because of this vegetation. Or you can say maybe gravels, maybe sediments, maybe rocks, any different types of bedding. I'm just giving you example of vegetation, but any type of bedding can cause the flooding because it will stop the river water to go as normal as it is when there is a heavy rain. Unfortunately, will increase the drag. The drag will stop the water flow velocity, or maybe slowing it down to cause this flooding. Now, how to use CFD to solve this problem? How do we know we are absolutely right by talking about this major problem? We need to use CFD. The CFD can help us whether if the raining causing slowing down the river velocity because of the vegetation, then we come up with the CFD. First, we design the mesh. So the software we use is the Ansys. You can use different version of Ansys. You have Ansys 16, you have Ansys 19. The one I use is latest one, which is Ansys R19.2. It could be even later, the version coming out very soon. This is updating only on the version, the current version itself. So it's better if you always update yourself with the softwares you are using with your work to be able to come up with more options. Now, look at the channel here. So if you go back to the first figure here, you see this region here where the vegetation is. It looks like this here. It's very, very, very dense, small, high mesh here. Now we design this channel. Imagine this is a river. We want to design it to see where is the problem, how we can design a channel to stop flooding so we can avoid damaging properties, houses, evacuating people or agricultural lands, and so on. Now, one cylinder we take as an example. Now I'm going back to the previous screen. This is one cylinder here, okay? So if I take a mesh design on one cylinder here, it looks like this. So I zoom in. This is the area around the cylinder. We have a lot of drag of the area. These cylinders we said is like vegetation. So consider the cylinders are vegetation. Now the vegetation, because they have drag, very high drag coefficient, then they will stop the river velocity, the water velocity, or the water speed to slow down. When it's slowing down, then it will cause flooding. It will come out of the river channels to the left and the right, then will cause damages. Now, this is another view of the mesh. You know, when you want to design a mesh, you need to make sure, as I mentioned earlier, to use the CFD work properly to come up with accurate results by having a very high resolution mesh. If you don't have a high resolution mesh, you will not be able to come up with very accurate results. Now, what we have done here, we cut the domain where the cylinders are. So I'm going to show you how. Here, at this picture, I'm going to cut from here, okay? I will cut this into two pieces. I want to see inside of my mesh how I have done, and it looks like this, okay? Now is a very good mesh where the cylinders, the vegetations are, as you can see. It's very high resolution with very high numbers of elements, millions of cells being used to design this mesh. So the element number, the node number is very high. Now, when we look at the animation, so the simulation works look like this. These are the cylinders. That's where the velocity, it can be seen. As you can see from these cylinders here, you see this very light blue color behind the cylinder. That's where the drag is, okay? Now, the drag coefficient. So let's say if you have the direction of your flow from here, that's where the drag is, yeah? Okay, so the first row of the vegetation or the cylinders or the rocks in the river will try to slow down the water. So why? Because there is very high drag. Like the third law of Newton, it says for every action, there is a reaction. So the water action has this cylinder's reaction to cause the drag to slow down the speed or the velocity of the river, then causing the problem as I mentioned earlier. Now, look at here. If we pick a point here, this is the streamline. So you look at the river from this angle. So if you are standing here, you look at the river from this angle, you see there is a lot of vegetations in this river. It could be anywhere in India because of these high numbers of vegetation inside the river, in the depth, in the deep beneath of the water. Then if you pick one point here, you see how high the drag is when the streamline velocity goes through the river. Now, in experimental work, normally we say this is intel, this is the inlet, and this is the outlet. You have an inlet of the channel and outlet of the channel. By the way, open channel compared to closed channel is, closed channel is like a pipe. There is no atmospheric pressure because it's closed. But the problem with open channel, that's why I use it as an example, is the pressure, the atmospheric, the weather condition will cause in the rivers and the channels, because open channels cases are more complex than the closed channels or pipe channels. Now, you see, clearly can be seen the contour lines when the river goes, the water goes through the river like this, okay? Now you see lots of drag here where the cylinders are to slow down the water. This is how we can investigate the problem, and then we change the design of our channel by considering more drag and all the other parameters that they are causing the slowing down of the river. You see, if you have this view of this channel here, this is just a Flume channel, the one that we designed, but consider it as a real river. When you stand in here and the water flow goes from this direction to end direction, you have lots of different bedding in the river. You will see it will increase the water, then it will cause flooding. That's how it looks like in simulation work. Now, if you look at a side view of the velocity, so you stand in here, and this is your river. We have lots of small trees and grasses or vegetation inside the river. We draw the velocity profile by this picture. So we use the circle ball as to demonstrate the velocity profile. That's the speed. When the flow comes in, it will hit the vegetation, and because of the drag, it will looks like this. It will bend, looks like this. So it will slow down. If we didn't have this cylinder, this vegetation in the river, how does it look like? It looks very smooth and straight like this, yeah? All the way go through. But because we have this barrier, it will slow down the speed of the water, okay? And it looks like this. So it comes up, then it goes flooding. It comes out of the river to the right, to the left, causing damages and disasters. Now, the understanding, the outcome of this presentation, I'm trying to be brief, not to go into deep detail, because we want to have some time for your questions and open sessions of answers, is for you to make sure that when you want to use the CFD, you need to know how to analyze and interpret the results. If your results are wrong, then you overcome this problem by doing it. So you need to have a good idea about fluid dynamics in general, and then be familiar with general physics, as I mentioned, and be good in mathematics to overcome these problems. And in my opinion, this is my last statement sentence I put, I will say CFD only validates when you have accurate data. You can't use a wrong data to validate your CFD model. You need to first have a correct data, correct geometry, then use the data, use the geometry to make sure and have a clear understanding of the comparison between your mathematical experimental work to your CFD work as a numerical to come up with clear, accurate results.